Sounds like a volume draft. I only heard a couple people talking. My main goal in this warm-up session is for you to get to talk to your neighbors. So my main request is that you don't just sit there silently, at least talk to your neighbor. If you've already read through the questions, you're not quite sure, you can ask each other how they do it. Right? It's a way to start the class. Okay, so first of all, what does f of x represent? And there's so few of you in the class, and I have so many questions, I can call on everybody almost for one question. So what does f of x represent? I'll go with volunteers first. Wait, Nanda. The height. Yeah, it's the height. Exactly right. It's the height. And what's another way of saying it's the height? What does f of x represent? Yes, Joshua? Yeah, the y value, the y coordinate. All right, super duper. Okay, and then what does f prime of x represent, Jared? Yeah, f prime of x represents the slope of the function at that y value. So it's telling us the slope every single time. Okay, and then what does the integral, the log s of f of x represent? What does that one represent, Sarah?
The area of the curve.
Yeah, the area underneath. Now, I often say the area under the curve, but what I really mean by that is the area trapped between the curve and the x-axis. So the area could be above the x-axis, it could be below. The key is that the area is being trapped between the function and the x-axis. So that's the area that they're calculating. Okay, what is the verbal definition of slope? So not the formula y2 minus y1, but what's the verbal definition? Like how you communicate conveniently with another human. Josh? Yeah, up, down, or the right edge. So that's how we conveniently communicate to other people. First, I got a treasure map. Like, if you had a treasure map and you're like, here you are, and you want to get to the treasure, you would say up 8, right 7. You know, it would just be simple, casual language. Okay, what is the meaning of the slope of a distance versus time graph? So remember, we are often going to look at a distance versus time graph. And so if we're looking at a particular curve in there, and we look at a particular point, and we say, what's that slope right there? What does that slope represent? Thank you for your enthusiasm. I'm calling somebody else. Who would like to tell us what the slope represents? Yeah, what was it?
The tangent, or
well, that's true. We're looking at the slope of the tangent line. We're looking at the slope right there. And what are the, for instance, what are the units of the slope? The up-down unit is distance, so that's distance. And then the right-left unit is time. And what is distance divided by time? Yeah, it's a rate. It's a velocity. It's a speed. So you can say velocity, or you can say speed, or you could say rate. I mean, a slope is always a rate, for sure. And we get that from remembering the formula d equals rt. Distance equals rate times time. If you solve for r, you divide both sides by t, and sure enough, you have that rate is equal to distance over time. So when you look at a distance versus time graph, the slope is actually a very interesting thing that you're calculating. You're calculating the speed of that object. Okay. What is the difference between a secant line and a tangent line? Ollie?
the secant line is 2 points.
Exactly right. So let me draw a little function here. And if I wanted this line right here, that's a secant line. And how do you know it's a secant line and not a tangent line? Oh, you already said it.
Yeah, there's 1 point.
Well, for the secant, yeah, you have 2 points. So the secant line cuts through 2 points.
Yeah.
Whereas, what's a tangent line? Oh, yeah, it's just 1 point. So wherever that may be, I mean, it could be this right over here, right? So there's my tangent line, and that only cuts through at 1 point. So before I move on from that, this, how do you calculate the slope between 2 points? What's the formula? Yeah, the slope formula, which is m equals y2 minus y1 over x2 minus x1. Whereas, what's the formula for calculating the slope at 1 point? Yeah, we don't have it yet. That's calculus, right? Calculus, at least differential calculus, derivative calculus, is the tool that allows you to calculate the slope at a single point. So your whole childhood, you go through life calculating regular slope between 2 points. When you get to calculus, you can find the slope at 1 point, and that's what we do. Okay, and then finally, what's the difference between average velocity and instantaneous velocity? Which one of these would be your average velocity? Yeah, the secant is your average velocity. That's your average velocity between 2 time periods. Like this is maybe time 2 seconds, and then this is time 10 seconds. Whereas which one is your instantaneous velocity? Yeah, the tangent line. Now, what's interesting about this? What's interesting about this is in your car, when you're driving your car, what does your speedometer show you? Your average velocity or your instantaneous velocity? Instantaneous, right? So like when you're in your car and you're looking at your speedometer and it's pointing at, say, 70 because you're on the freeway, that's your instantaneous velocity. That's how fast you're going right now, right? So like when the officer says, do you know how fast you were going? Well, yeah, man, that's what your speedometer was showing you the whole time, right? It's how fast you were going at that moment. Wouldn't it be weird if the speedometer in your car showed you your average velocity over the course of the whole trip since you started? It would not be helpful at all, right? Like if you're in traffic, you're taking busy traffic and you're heading to work, and you're like, oh man, my average velocity is 20 miles per hour. Because overall, with all the stop and go traffic, your total velocity, your average velocity has come down quite a bit.
My mother actually has a car, and this is average. Like, it shows for average. And
Oh, it does?
Yeah, it does.
Oh, that's
for average.
interesting. Okay, like it's a new car.
Yeah, it's a new car. And then, well, my car, it actually reads this. So I was like, where does, I wasn't like paying attention, like it actually, like you have to read it, like it's all like numbers and stuff. And it kept saying me average. I'm like, I don't know about my average, I want to know how.
Yeah, exactly. Now you might want to know your average velocity, like if you're driving across country. Like I've driven across the country many times. I've driven to Ohio from Arizona, or I've driven to Montana from Arizona. And you are generally curious to know about how long it's going to take you to get to Montana or Ohio, because you want to break up your day, right? How far can I reasonably get today? And you throw out some number like, I bet I can average 65 miles per hour. Like, do you really average 65 miles per hour? I don't know, but that's the vision you tell yourself, the lie you tell yourself when you start the trip. So like, okay, today I'll go from Arizona to Utah, and maybe that's how far I'll get today. And then the next day we'll go from Utah to Monday, something like that. Okay, well, wonderful, folks. So these are all the different concepts that we're talking about. That's the warm-up. So here's our calendar. I did update our calendar. This is not the right calendar. So I didn't update it on my screen, but I did give all of you the updated calendar. So I bet if I just go back, I can show us the real updated calendar, which is, yeah, here we go. So today's January 22nd. We're due to do chapter 2.2 as soon as we finish chapter 2.1. And then we just keep on plugging along, right? The next few weeks of class, we just keep learning new material. And then finally, we take our first test on February 12th. Yeah, oh, it'll be okay, because I have a practice test for you, and the practice test, I will also post solutions to the practice test online. So you can take the practice test, you can look at the solutions. That in and of itself is an assignment. You have to turn it in for a grade. So you have to do the practice test, and you'll feel very confident about the test by the time you do it. Okay, so that's where we are. And let's see, I feel like, did I forget to tell you a joke last time? No, I've been telling you jokes. Okay, Rosa.
The 2.1 is due today?
No, it is not. I believe in the last class, at the end of last class, I told you it would not be due today because we didn't finish it last week. And I went into the Moore system and I extended the due date until next Monday. So you technically have nothing due today. Now, we are going to finish 2.1 today. So I do recommend that you go home tonight and finish it, because that way it's fresh in your mind. Okay, so here we go. I do have a joke for you. When did the man go to the dentist? When did the man go to the dentist? At 2:30. 2:30. All right. So first of all, before we get going, does anyone want to ask any questions about more? Any of the homework? I think I've gotten messages from almost all of you. I haven't actually gone through and checked off who wrote me messages and who didn't. But does anyone want to take a look at more? Any questions at all from section 2.1 that you've been doing at home? Any questions at all you want to ask about the system or how to type things in?
Can you go to the last question, number 8?
Yeah, number 8. Yeah, now we haven't gotten to this one yet in our packet, but so let's just hold on. We're about to get to a problem like this. So we'll see that then. Any questions about things that we've already done? We did that question. We're doing that now. Yeah, how about we'll hold questions until we actually finish doing all of them. So here we are. The last time we left off here
I have
at.
another question.
Oh yeah, go ahead, Rosa.
Are the videos, I know you said that you recommend us to watch the videos.
I do.
Are they graded, or do you grade us?
No. Well, first of all, this video button, this is just if you want to. So you're looking at the problem, you're trying it on your own. Let's say you get the wrong answer, you're like, oh, remind me. So you click on that video. What you do have to do is right here within the section 2.1, it says textbook, video, assignment. You do have to click on these video assignments, and you do have to click on each one and click this little check mark that says I've completed this section, and then click submit. And then you go to the next video. And then, you know, theoretically, you click play, you watch the video, or at least you scan through it to see what they're talking about, and then you click the box that says I've completed it. Hit submit.
Okay.
So these videos, yes, you do have to do.
Oh, that's the video.
Yeah, that one you do have to do. This video within the assignment, there's always going to be a video button. That's just for you if you need the extra help. It's there, and it's going to walk you through that problem. So it's not like some video about anything. It's about that problem. Okay. Well, then this is where we left off last time. And I don't have the data, but perhaps someone could simply share with us what was your final decimal answer for each of these. So would someone feel confident about sharing? So first of all, you have f of 4 minus f of 3 all over 4 minus 3. And then you got some decimal over 1. What was this decimal? 28.19. Okay, great. So what that means is on this graph, if we're looking at a function and it looks something like this, and we're going between 3 and 4, let's just make sure we're all looking at the correct graph. So I don't know if I've shown you Desmos yet, but Desmos is a wonderful online graphing calculator. It's the best one I've ever used. So 34x minus 0.83x squared. And then I can zoom out. Here's my graph. And change the window a little bit to go up higher. I did 300. I did 400. I did 500. 600. 700. Okay, that's a little better. And we want to zoom in to around 4 seconds. So here's 4 seconds. I'm going to make it a little higher. 200. There we go. So we're looking between x equals 3 seconds and x equals 4 seconds. So you see these 2 points right here. This is the slope that we're calculating. We're calculating the slope from 3 to 4. So just so everyone understands, that's what we're actually doing in this problem. We're saying, here's our original parabola, and we'd like to find the average slope, that is the secant slope between time equals 3 and time equals 4. And so you can imagine, I mean, that already looks like a fairly straight line right there. It is curved, it's hard to tell. But we're finding the slope of this line right here. And everybody, you just said the answer was 28.19 something? Okay, well, that's good. Okay, so then you moved on to the next problem, and it was f of 3.5 minus f of 3 all over 3.5 minus 3, which meant then you had 0.5 on the bottom, and what was this decimal? 108.832. And then when you divided by 0.5, what did you get?
No, you have to do minus.
Sorry, what? What am I changing?
Well, the whole answer is 28.605, but it's not over.
Oh, you're just saying that's the final answer?
But if you were to do the full, I think it's 108.8325 minus 94.
Oh, okay, does anyone have that intermediary answer? Okay, it doesn't matter. Okay, you can just tell me the final answer then. The final answer was? 28.605. Okay, great. All right, and then what about this next one? We did f of 3.1 minus f of 3 all over 3.1 minus 3. And what was that decimal? 937? Okay, great. Now, folks, already, what are you noticing about these numbers? Yeah, they're fairly similar to each other, but they're increasing just a little bit. And let's see why that would be. See, if I go from this point to this point, I'm just going to claim that that's my 3 and that's my 4. If that's my slope, all the way from 3 to 4, then this slope, that's the starting slope, but we're going to call that 28.1. But then I moved this point closer. I moved it all the way closer to 3.5. And by moving that point closer, what happened to the steepness of my line? Yeah, it's a little steeper now because I moved closer. And that was the next slope, which is 28.6. And then I went ahead and I moved my point even closer to 3.1. Just getting kind of small. And so now I'm at here. And now when I draw that slope, it's even steeper still, right? And that's how we got the answer 28.9. Okay, so every time we move our point closer to 3, the slope is getting a little steeper. Is it going to keep getting infinitely steep? Because at some point, this point and this point are going to be right next to each other, and we're simply going to have a tangent slope. Right? So as soon as I get this point infinitely close, I'm merely going to have a tangent slope And that tangent slope is the slope at one point. Okay, so let's keep writing down our answers. What was the next one? F of 3.01 minus f of 3. What was that slope? 28.9 what? 28.90. It should be a little bigger than that.
29.07.
29.
Oh, 29. Okay, there we go. 29.01. Okay, well that's good. So we're continuing to get bigger and bigger. And then the last one, f of 3.001 minus f of 3. What did that turn out to be? 0.19. Okay, so it seems to be getting pretty settled right around that value. Okay, well now that's the whole idea. What we just did in this problem was we said, if you take the slope between 2 points, that's a secant slope. It's an average slope. And if I hold this point fixed, right, because we held the 3 number fixed, not the whole thing. We were always using a beginning time of 3. But then the second number, I started to bring it infinitely close. Now, where's Mr. G coming with this whole infinitely close business? I mean, I only brought it from 4 to 3.5 to 3.1 to 3.01 to 3.001. But the idea would be, what if you did bring it infinitely close? What if the next slope that we found was f of 3.00000 minus f of 3 over 3.00000. And then what would that be? Now I realize even this isn't infinitely close. The distance from 3 to 3.001, you know, you can measure it. But what if you did, in your mind, do a thought experiment, and you bring the 2 points infinitely close together? Technically, it's still 2 points, but they're infinitely close together, so they're technically 1 point. This is a little bit of philosophy. If you bring 2 things infinitely close together, it's technically 1 thing. Because how far apart are they? You can't measure how far apart they are. It's infinitely small. A number that's infinitely small is essentially 0. That's a little bit of the philosophy behind calculus, is that when we say something's infinitely small, it's a positive number. It's infinitely small, but it's positive. But because it's infinitely small, it's 0. So you can let yourself wrap your mind around that whole idea, that in calculus, we deal with things that are infinitely small, and we say it's 0. Now, is it actually 0? No. It is a positive, infinitely small number, but it's essentially that you can call it 0. Okay, well, that's that problem. Whatever we get down to here, you know, if you keep on going and going and going, eventually you get to a number that would be called the answer. We didn't get there yet, but we just saw, you know, how you approach that type of thing. Okay, any questions about that particular problem, folks? What we were doing there was introducing the idea of what we will do in calculus, which is calculate a secant slope between 2 points and bring the 2 points infinitely close together, and that's how you find the slope of 1 point. And in fact, going back to this, okay, how do you find the average slope? You use the slope formula. How do you find the instantaneous slope? You use calculus, i.e., bring 2 points infinitely close together. And that's the technique. All right, yes?
So there's no actual.
Yep, there's no actual formula. It's still a slope formula. That's a great question, Josh. It still is the slope formula. The 2 points are just infinitely close together. Yeah, is it? I mean, does it seem cheesy? Does it seem cheating? You know, somebody in the 1600s was like, make them infinitely close. We'll call it 1 point. Right? That's kind of what they did.
Why can't they just do it?
Right, well, very good question. Can you do the slope formula when it really is the same point? So let's say you have here, and you have this coordinate, which was 3, and then let's just say the output was 6 to make it easy. Can you do the slope formula with the same coordinate twice? Because if I did use this same coordinate twice, what would happen? It would be 3, 6 is one of the coordinates, x1, y1. 3, 6 would be the other coordinate, x1, y1. I'm sorry, x2, y2. And if you do use the same coordinate twice, you end up with 6 minus 6 over 3 minus 3, which is 0 over 0, which if you type that into your calculator, what do you get? Not 0. Undefined. You get an error message.
But there's nothing there to the thought, so we're not just using.
No. But I challenge you to type it in your calculator.
No, because it only knows as much as it was put in, but still.
Well, that's true. Well, it's a very interesting idea. Here, I appreciate your philosophical question. Everybody, let's try. let's say that we wanted to claim that 0 divided by 0 actually did equal something.
0.
Oh, you want to say it's equal to 0?
Yes.
Right, okay, I suppose we could try that. Let's say that 0 divided by 0 was 0. If you made that an assumption in mathematics, it would lead to some sort of contradiction that would make other things incorrect. Ultimately, we don't say that 0 divided by 0 is equal to anything. We say it's undefined. It'd be like saying, what's 3 plus apple? What number is 3 plus apple equal to? Is it equal to 7? That would make no sense, right? So this is also undefined. You can't just add 3 plus an apple. It's undefined. It makes no sense. 0 divided by 0 is undefined. It makes no sense. But again, Josh, don't take my word for it. Mull it over for a while. Go home and journal about it. Go home and draw about it. See what you come up with. Because that's an interesting challenge in and of itself, is to convince yourself that 0 divided by 0 has no meaning. Okay, wonderful folks. We're done with that problem. Let's keep going. All right. Now, the next question is twofold. We actually have 2 problems to do here. And the problem's way up there, but I'm just going to write it right here on the board. But what they're asking us is to find the average rate of change of that function on the interval 1, 2, and then later on the interval 1b. So first of all, and remember folks, always what's the first thing we do? Draw a picture. So I'm going to go ahead and show us Desmos real quick, because Desmos is very helpful. It just helps us get an idea of what the picture looks like. So here's my 9x squared, is it minus 7? Okay, there's my graph. Yeah, 9x squared minus 7. You can see it goes through the axis. Oh, that's not very friendly, at 0.882. It has a y-intercept of -7, and it starts going up and up and up. So let's draw that. The y-intercept is -7, the x-intercept is 0.882, and it's just a parabola that's going up. So let's begin by drawing that picture so we can see what we're doing. So again, the y-intercept was -7, and then it was up like this. The x-intercept was 0.882. The graph goes up in both directions. The left-hand side doesn't really matter, because we want to know the interval from 1 to 2. So let's draw the number 1, draw the number 2. Make sure your graph goes that far. No? And so now I have the coordinate at 1, and I'll have the coordinate at 2. So there's our first drawing. We're looking at the function 9x squared minus 7. And we want to know what is the average rate of change on the interval from 1 to 2. Now remember that interval from 1 to 2, they're saying when x equals 1 and when x equals 2. So on the x-axis, we have x equals 1, x equals 2. We take those 2 points, and we draw a line connecting them, and that is our secant line. So as you draw that secant line, keep in mind, the parabola is curvy. The parabola is curved. The secant line is straight. Right? The parabola is curvy everywhere. A parabola is always curvy. There's not one part of that parabola that is straight. It's all curvy, but the secant line that I just drew is a straight line. And so we'll solve this problem the exact same way we did the previous one. If we want to find the average rate of change, I'll just say the average slope, on the interval 1 to 2, then we'll say m equals, and we're going to use the formula that we had before. Remember our formula, I'll write it down over here so I'll remember it. So the formula is f of b minus f of a all over b minus a on the interval a, b. Right, so that was the formula we came up with. It's just a quick, easy formula for telling us the secant slope of a function on an interval. So if this is our a value, this is our b value. And so we have f of b minus f of a all over b minus a, and we plug in the numbers f of 2 minus f of 1 all over 2 minus 1. So this formula here, f of b minus f of a over b minus a, that is our formula for secant slope. That is our formula for any function. Secant slope of any f of x. And so, I mean, that's a formula to lock away in your memory. Now, this formula is actually just the slope formula, y2 minus y1 over x2 minus x1. But we use the values from the function. All right, so what is it? How do I calculate f of 2? We just plug 2 into that, right? So if I wanted to show a lot of work, I would write down this. I would say 9 times something squared minus 7, 9 times something squared minus 7, where here I plug in 2, and here I plug in 1. All right, so that would be if I wanted to show the work. I'm plugging 2 into the function, which is 9x squared minus 7. I'm plugging 1 into the function, which is 9x squared minus 7. And on the bottom, 2 minus 1 is 1. So we're done here. And so what do we end up with? 2 squared is 4, times 9 is 36. 36 minus 7 is what, 29? And then 1 squared is 1, times 9 is 9. 9 minus 7 is 2. So now I have 29 minus 2 over 1. And so it's just 27 over 1, which is just 27. So that is the average slope on the interval 1 and 2. And theoretically, you know, let's not simplify it down to 27. Let's just leave it as 27 over 1. Because the slope is fundamentally a fraction. So that's it. If I were to actually find this secant line right here, I would say, hey, that slope is 27 over 1. Up 27, right 1. Up 27, right 1. That's the slope of that secant line. And that's what we just calculated. Yep. Now you might say, oh, that's not very exciting. But what if I said f of x was your miles per hour as you take off from a stoplight? Right, so you're at a stoplight, and then you take off, you put your foot on the accelerator, and you start speeding away. And so I'm saying between 1 and 2 seconds after you left the stoplight, how fast were you going? 27 miles per hour. Because remember, a slope is a velocity on a distance time graph. Okay, Rosa.
So what if you do with the other people?
Now we're about to do that one. So now, second problem. Now find the average slope on the interval 1 to b. Now what on earth does b represent? B is not a number, it's a letter or a variable. It represents any time. Right? So again, if we're saying this is your distance versus time graph of you leaving a stoplight in your car, then b is just some number of seconds later, right? We're about to calculate your average velocity after leaving the stoplight between 1 and b seconds later. So it could be 2 seconds later, but b can technically equal anything. So that's it. We're just allowing ourselves to do the same process with a letter so that when we're all done, instead of having a number, we're going to have a formula. And that formula will automatically tell us your velocity after b seconds. And you can let b do whatever you want. So let's try it. So m equals, same formula, f of b minus f of a. I always find it helpful to start with formula. And now this is my a, this is 1 is a, and b is literally b. So we're going to have f of b minus f of 1 all over b minus 1. Okay, now, folks, for the next couple, about a minute, you might feel a little uncomfortable. Right? We're about to do some algebra. We're just going to do some algebra manipulation. And now is as good a time as any to tell you that the subtitle of this class, so what are we all in? mat213, business calculus. The subtitle of this class is Advanced Techniques for Algebraic Manipulation. Okay, kind of abbreviated there. So the subtitle of this class is remembering all the algebra you've ever done in your whole life and using it fluidly within context. Advanced Techniques for Algebraic Manipulation. That's the subtitle of our class. So what we're about to do is, first of all, let's go ahead and find our formula here. So f of b, again, is going to be something minus something, where the first formula, the function is still 9x squared minus 7. So that's 9 something squared minus 7. 9 something squared minus 7, where first I'm plugging in a b, and then I'm plugging in a 1, and all of that is over b minus 1. And what I'm telling you is we're about to do a whole lot of algebraic manipulation, which for some people it sometimes can cause nausea, you might feel dizzy, you might get dry mouth. Who knows? I'm just kind of being funny here. The point is we're about to do a lot of algebra. So let's try it out. What do we have? This is just 9b squared minus 7. Then we're going to subtract, what's this thing? So 1 squared is 1, 1 times 9 is 9, 9 times 7 is 2. So now I just subtracted a 2. All over b minus 1. So far, so good. Then what can we do? We combine like terms, so this is really 9b squared minus 9, all over b minus 1. Then what can we do? Well, we don't have to do the quadratic equation. We do have a squared term in there. And when you see squared terms, a couple thoughts should come to mind. One is the quadratic formula. Another thought that comes to mind when you see a squared term is factoring. Right?
Where'd you get the 2?
That's what 9(1) squared minus 7 equals. Because remember, I took my function, 9x squared minus 7, I plugged in a b and I plugged in a 1. Okay. So one thing that we think about a lot in advanced techniques for algebraic manipulation is factoring. You have to remember all the tools you ever learned for factoring. Okay, so what can we factor out of the numerator? We can't factor out of b yet. We can factor out a 9. So now we have 9 outside of b squared minus 1, all over b minus 1. Okay. Now what can we do? Can we do anything with the b squared minus 1?
Yeah.
What? You have b minus 1, b plus 1. So remember, we have a special technique where if you have a difference of 2 squares, a squared minus b squared, that's called the difference of 2 squares. That's really a minus b times a plus b. That's just a formula for difference of 2 squares. You can also call that, say, x squared minus 25. If you have x squared minus 25, that's going to be x minus 5 times x plus 5. Does that ring a bell? It's just a factoring technique you learned at one point in your life, and it's part of our advanced techniques for algebraic manipulation. So remembering everything that we ever did, now this becomes 9 outside of b minus 1 times b plus 1, all over b minus 1. Now what? Here we get to cancel out the b minus 1s, and we're left with 9 times b plus 1. And technically, all over 1. And that's it. That's our answer. The answer is 9 times b plus 1 over 1. Now you might look at that and say, okay, well, we're done simplifying. What on earth did we just calculate? So first of all, what is this thing? It's a formula for a slope. Exactly right. So it is a formula and it's a slope. And what we're saying is, if you tell me the value of b, you just plug it in this formula and it'll tell you the slope, the average slope from 1 to b. So for instance, I'm just going to continue my graph here. Here's b way up here. Here's my f of b, whatever that might be. And I'm saying, whatever slope now I choose to draw from 1 all the way up to b, this formula is going to immediately calculate that slope for me. Yeah, let's plug in 2, because we already know the answer for 1 and 2. So if I plug in 2 right now, what should I get? I should get 27. So let's try. If I do 9 times 2 plus 1, that is 9 times 3 or 1, which is 27 and 1. So does the formula work? That's it. That's it. We just came up with a formula for the slope for any interval starting at 1. And now you can plug in any other number for b, and it will tell you the slope between those 2 points. Yep, between 1 and whatever other point you choose. Yeah. Now we can immediately do a bonus question here. What if I choose a point infinitely close to 1? Right? Because if I bring this point infinitely close, then that means I'm about to calculate a tangent slope. So what if I plug in a value that's infinitely close to 1? Right? Infinitely close to 1. So first of all, on a number line, here's 1, and here's 2, and here's 1.5. What number is infinitely close to 1? 1.1 at the end, right? That number would be infinitely close, provided I put infinitely many 1s. So what does this formula do then? If I put in 9 times 1.01 plus 1 all over 1, well, what's 1.0 roughly? 1, right? So we would just go ahead and call that 9 times 1 plus 1 is 2 over 1. And now that tells me the tangent slope is 18 over 1. That actually is the tangent slope. We can make that philosophical leap now that if I wanted the 1-point tangent slope, the 1-point tangent slope is 18 over 1. By making the mental leap, if you're willing to choose a number infinitely close, and just choose a number that's really, really close, and the number that you get is basically the answer. How do you feel about that? You don't like it? Well, that's okay. That's okay. This is philosophically new. Because really, what did I end up with here? That's 1.0 plus 1, so that would have really been 2.0. And then if I multiply that out, that'd be 18.0, which is roughly 18. Right, so as I continue to make that number infinitely small, this number gets infinitely close to 18. Okay, well, very nice, folks. That's that problem. You can see, first of all, are we doing anything other than the slope formula? I mean, we're just doing the slope formula right now, right? When you begin calculus, you just do the slope formula a whole bunch. And we threw in a variable, so we're doing a little bit of algebraic manipulation. But really, all we're still talking about so far is just slope. Any questions before we move on? Okay, let's try another one. Okay, these are conceptually easier. We've done all the major calculations for today, I think. So now we can rest a little bit. I'll leave that formula there. Okay. Now, calculus, the concepts are what are most important. So here we have a problem, and all we're going to do is answer some conceptual questions about it. It says here the graph of f of x is shown below. So everyone label this curve here, call it f of x. Now, what actually is f of x? What is that equation? I don't know. Did they tell us what the function was? We have no idea. But I'll go ahead and just take a guess that it's actually x cubed, say cubed in there, right? Squared. X cubed minus 1x squared minus 90x. I'm just guessing, okay? And it honestly doesn't even matter what the function is, but let's just see if I graph that, is it close? So x cubed minus 1x squared minus 90x. There, how did I do? Is that reasonably close to what we thought it would be? I'm going to fix this a little bit, negative 15.
Yeah.
Does that look like the graph? You know, charitably. It's not bad. So that's the graph that we're looking at. It even goes through the same roots, doesn't it? Like, does it go through -9 on the left? Does it go through 10 on the right? Does it go through 0? Not bad, right? Now, I'm not a mathematician. It's very simple rules that I just follow to make that formula up. We can make up formulas as we go through class to match the graph. But we don't need to. We can just look at the graph. So looking at our graph, the question says, estimate and list the values of x where f of x has a horizontal tangent. So, again, using your pen or your whatever you want as a slope indicator, what's the slope right now? Just say positive, negative, or 0. Positive, positive, 0, 0. There's one point where it's 0, so put a little dot at the maximum and say m equals 0. And now what's the slope? Negative, negative, oh, 0, 0. There's another point when the slope is 0. And then positive. Right? Now, if you wanted to make it really nice for the eyes, you can even write plus, 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 plus. As a reminder that as you move along here, the slopes are positive. And then negative slopes all the way to here, and then plus. It's a very helpful little visual, just to remind yourself what we're talking about, and what we're talking about is slope. Okay, so it says estimate and list the value of x where f of x has a horizontal tangent. So where were our horizontal tangents? Here, that's a horizontal tangent. Remember, your slope indicator is a tangent line. And we're looking for the horizontal tangent lines. So the one was there, and one was there. That's a horizontal tangent. For instance, if I drew a tangent line right here, is that horizontal? No, that's a negative sloping line. It's not horizontal. Okay, so what are our answers? At x equals -4. Wait, I'm sorry, I read that wrong. -5 and x equals 6. That's it, that's the whole problem. We will be asking over and over and over again, where's the horizontal tangent? And horizontal tangent is just one way to say that. So if you have here m equals 0, one way to say is that's m equals 0. You could also call it, go and write all these down. You could also call it a horizontal tangent. You could also call it, this is my favorite way to call it, a flat spot. Right, it's a flat spot. You know, if this is a hike that I was on, here I'm hiking uphill, I reach a flat spot. I'm hiking downhill, I reach a flat spot. I'm hiking uphill, so I like to call it a flat spot. The other thing that you could call it, this one up here is called a maximum. And so what's this one down here called? A minimum. So there's a lot of vocabulary words that we'll use to describe these very special points. In calculus, the max or the min, the horizontal tangents, the flat spots, those are very special points, which in calculus we simply call them critical points. Which is a nice name. It sounds like a skater dude. Like, it's critical. It's a critical point. And so these are critical points. They are the points where the slope went to 0. And so one of the ways you can write this is if f prime of x is equal to slope, right? F prime of x is equal to your slope. These critical points are when f prime of x is equal to 0. Right? Because we're saying f prime of x represents slope. Yeah, I'll say that again. These are the points where the slope is 0. Right? Because remember, this is positive slope, this is negative slope, and this is 0 slope. So if I want to know when is the slope 0, well, first of all, I would go take a look at my f prime of x formula, because f prime of x is always telling the slope. And I'm interested in the critical points, which is when the slope is equal to 0. And so I just let f prime of x equal 0. And that literally means I'm looking for when the slope is equal to 0, which is a horizontal line. So this formula right here, f prime of x equals 0, we're going to do that all the time. We're going to say, let f prime of x equal 0. But what are we really saying? Find all the points where the slope is equal to 0, which means find all the points where the slope is a horizontal line. Right, like if you set f prime of x equal to 0, what x value can I plug in? Good question, Rosa. What x values can I plug in such that f prime of x would be equal to 0? You can either plug in x is -5 or x is equal to 6. If you plug -5 or 6 into the f prime formula, the answer will be 0. Yeah, really good question. That's a nice way to think about it. Okay, so was this problem hard? No, you just had to find the maximum and the minimum. But this was a good review of vocabulary, all the different ways that we can talk about this. What questions would you like to ask? Anything at all? Rosa, thank you for your question.
So for like,
Yes, Henry.
we learn like solution set.
Oh, yeah, you can. We will use interval notation. I think we'll use it in the next problem, actually. Yeah, so in this problem, the solution set would simply be the solutions are the set of the numbers -5 and 6. So since it's just two values, we would just use a set brackets. But thank you for leading into the next question, Henry. I didn't pay him to do that. Wait, actually, no, it's not the next question. I take it back. But we'll eventually get to interval notation. All right. Come on, folks. Doing. So number 8 has 2 questions. Again, these are just purely conceptual questions. These are questions that anyone with a knowledge of positive, negative, and 0 slope would be able to answer. There's no real calculus involved yet, but these are the concepts of calculus. So number 8, consider the graph of the function above, well, below. So there's our function. What is the sign of the slope of the tangent line at the given point? So at this point right here, draw your little slope indicator, your little tangent line. Keep in mind the tangent line would look like that, right? It's a line that's tangent to the curve. And so what's the sign of the slope? Negative. That's it. Now, this second question here, this is an error. the computer accidentally drew some extra bits right there. We're just looking at this function. So now you're drawing your tangent line. What's the slope of the tangent line? Positive, that's it. Okay, now at the beginning of class, who was it that asked me to do the very last problem? Joshua. Okay, so here's the last problem on the more homework. It says, we have a graph here. This is our f of x, whatever that function is. We could make up a function. You know, we could even go find the function that actually produces that graph, but we don't need to. All they're really asking us to do is use the graph of f of x below, above, to estimate the slope of the function at x equals 2. So here's what you would do, folks, and here's what you can do right now on your own papers. What you're going to do, and what I'll do is, I'll use a straight edge. I get to use a ruler. You can just use another sheet of paper. I'm going to draw a tangent line. So use another sheet of paper or a note card, and hold that note card or piece of paper up to the curve, and make your best tangent line. The idea is that you're drawing a line that's parallel to the function at that point, right? So you want to push it right up against it, and I'm going to say that's my tangent line. And I'm going to draw a line all the way through the graph. So there's my tangent line. So everybody go ahead on your own. Use a straight edge or a ruler or a note card and draw a line. And it says, estimate the slope at x equals 2. Well, there, I've got my tangent line. That's the slope I'm interested in. And so I'll just go ahead and look at the graph and find some coordinates that would be easy to find my slope. So for instance, I'm going to use this coordinate. Now this is just me. You're going to have to choose your own coordinates. I'm choosing this coordinate, the y-intercept. I'm going to call that 0, 3.5. Okay, because I feel like my line cuts through between 3 and 4, so I'm just going to call it 3.5. And then I'll choose another point down here. I like this point right here, and I'll call that coordinate 4, negative 3.5. So again, I just chose two coordinates. I didn't see any coordinates that went straight through the grid, so I had to go halvesies. But does everyone basically agree with my coordinates? And is that roughly? It's an approximation, right? So now I'm going to find the slope from that point to that point. So I'm going to write m equals y2 minus y1 over x2 minus x1. And so I'm going to label my points. Always a good idea to label points so you know what you're looking at. That's my x1, y1. This is my x2, y2. Now I'll go ahead and plug everything in. Now your numbers are going to be different unless you're just kind of using my numbers, and that's fine. But your numbers would be different. Now I'm going to go ahead and do y2, negative 3.5. y1 is 3.5. x2 is 4. And x1 is 0. And now I have negative 7 over 4. That's my slope. Negative 7 over 4. Roughly speaking, at this point on the graph, the slope right there is approximately negative 7 points. Now keep in mind, the problem just said use the graph to estimate the slope. Is my answer correct? Yeah, to within a certain approximation. It's not accurate. If I wanted to be accurate, I would have to actually know the function. I'd have to know what f of x was. I would actually have to do calculus, find the derivative, and then I would actually have to plug in the x value of 2, from 2, and then that formula would spit out the actual slope for me. Again, to find the actual answer, I'd have to know what the actual function was, do the derivative to find the slope formula, and then plug in x equals 2, and then that would tell me the real answer. All I did was just come up with an approximate answer. So when you get to this problem on your homework, this is, I think, the only problem in your homework where it's going to be like this. You're going to go into more, and you're going to get to problem number 8, and it's going to say, use the graph to estimate the slope at x equals negative 1. So what I would probably recommend you do is, A, you could just print this problem out. If you printed the problem out, then it's on a sheet of paper. You can use a straight edge, and you can find the slope. If you don't want to do that, you can hold a sheet of paper. Thank you, sir. You just hold a sheet of paper up to your graph. The computer screen will shine through your paper, and you can do it that way. You could trace the grid onto your paper, choose the point we're looking at. What are we looking at? We're looking at this point right here for this problem. It says find the slope at x equals -1. So I would, on my paper, trace in the line. I'm not going to do it on your paper today. I would trace in my tangent line. Or even better, you can just hold your straight edge up against your computer screen. There we go. You can just hold your straight edge against your computer screen and just try to find a couple points that it goes through. Don't write on your computer screen, obviously. But you know, you just say, okay, well, this point's roughly speaking -2, -0.5. And then over here, this point is roughly speaking 2, 1.5. And then that's it. Once you get your 2 points by holding your straight edge up against the screen, then you can go ahead and calculate the slope. In which case, my slope is going to be 2 over 4, which is half. And then I look at that and I say, is that roughly up 1, right 2? And in fact, check this out. Look at those 2 points. Up 1, right 2. Up 1, right 2. It's definitely up 1, right 2. I'd say I got a very good approximation. Okay, we'll go there. Folks, we did it. That's the end of section 2.1, which is timely because my phone just went off saying that we can take a 10-minute break. So before we break, would anyone now like to ask any questions about this homework? Like Joshua, you were asking about this one, right? Does that answer your question? Yeah, so you'll just have to hold the straight edge up to your computer screen and choose some points. Otherwise, folks, the remaining questions on 2.1 are just like what we just did. And if you now have your notes, you can go home, use your notes, and do your homework. My one recommendation for you is that you have a lined notebook that you're solving these problems in, and you label it assignment 2.1, number 1, and you show all your work, and then you type in the answer. And then you go to number 2, show all of your work, type in the answer. Because you want to have a journal. You want to have a journal of your journey through these problems. If you just have scratch work and then you throw it away at the end of every day, that's not going to help you much. You really want to have a really nicely labeled.
Can we print out the whole question?
Oh yeah, check it out. You've got this print version right here, and you can click on print version, and it will print out all the questions for you. You can print that out, show all of your work right there on the page, and wow, now you'll have a really good record of all of your work, and you don't even have to mess around with a sheet of lined paper. You can just print it out. Yeah, Rosa, so by all means, if you want to print it out, I won't collect that from you. It's just your own personal work to keep forever and give to your kids. Okay, so there we go. Let's take our break, and then we'll start section 2.2. I think everyone already grabbed the packet from 2.2. So let's see what time it is. It's 11:55. Let's be back in the room at 12:05. If you have any questions at all, for the next 10 minutes, I'm not on break. You're on break. So if you want to ask me questions, come ask me questions. You're still paying me for the next 10 minutes to be here for you. I'm not on break. You're on break.
What do you do before class? You say you come like a half hour early, usually?
Yeah, I was in here probably just 15 minutes early today. But yeah, I mean, I'm up I come to campus, I go up to my office, I do whatever paperwork, and then I come here a little early, and then I'm just setting up the room.
What is there on class and my middle class? But I just come.
Oh yeah, you can just come up to my office. You know, provided it's in my office. Yeah, you can always go up there. If I'm not there, you can just sit outside the door. You know, work, whatever you want. Yeah. Well, I hope not. I would prefer you to slip money on me. I mean, that'd be my preference.
Mr. D.
Yes.
Sign this paper.
Yes, sure. Like I said, I can sign it every day, or you can always just give it to me and, well, I guess this is the end of this week. So, oh no, it's not the end. Yeah, we can just do it once a week. And I'll sign both. All right, it's 12:05, folks. Let's keep going. I'm still outside. I'm just gonna do the holler. So everyone, take out your 2.2. One back, folks. Now, we've spent a couple days now talking about slope. And what we're about to do has very little to do with slope. Rather, it begins with the whole idea of what a function is. A function is input output. So let's start with right here from the top where it says typically. Typically, when you talk about a function, you say, when x is something, what is y? So let's just look at this function that they gave us, and we'll do an input-output table just right here. You can make a little one. So there's x, there's f of x. So let's just go across the grid here. When x is 0, what is f of x? 5. All right, so input-output. If you input 0 into this function, there's 0. If you input 0 into this function, the output is 5. So input-output. If I input 1, what is f of x? 3. And if I input 2, f of x is 0, because it's right there at the bottom. So there's input 2, output 0. If I input 3, f of x is 1. And if I input 4, f of x is 2. And if I input 5, f of x is 4. Okay, so very simple. It's just the idea that a function is input-output. So again, if I were to say, when x is blank, what is y? So when x is 1, y is 3. When x is 4, y is 2, and so on. In calculus, however, we talk about a limit. So when we talk about a limit, we're saying when x is close to a value. Typically, we say when x actually is the value. But in calculus, we're going to say, well, what if x is just close to it? Right? So let's just say that I go ahead and say x is really close to 3, like 3.1. Let's say x is really close to 3. And ideally, I don't want to say how close to 3. I just want to say really close. Okay? So if I say that x is really close to 3, and I come up here and I look at the point where that would be, then what is y really close to? 1. So effectively, we're still saying the same thing, right? So originally I said when x equals 3, then y equals 1. But what if now I change my language and I say, let's say x is close to 3, either bigger than it or smaller than it. So I could be just to the right at 3.1, I could be just to the left at 2.9. All I'm really saying is that if my x value is really close to 3, then what is my y value going to be? Really close to 1, right? And this might sound strange at first, like, oh, this is a technical calculus concept, huh? Really close to. All right, but that's exactly what we're shooting for. So if I'm really close to 3, either to the right or to the left, then my y value is really close to 1. And that's what a limit is. When we talk about limits in calculus, we're no longer saying let x equal exactly 3. We're just saying let x equal a number really close to 3. And if you do let x equal a number really close to 3, then y will equal a number really close to 1. How's that? It's almost like we're loosening up our standards. Like ideally, you would let x equal exactly 3, and then y would equal exactly 1. But we're saying, hey, in calculus, let's just get close. Now, who wants to take a guess? How close to 3 are we going to get? Infinitely close. So that's really what a limit is. We're saying if you get infinitely close to 3, but not equal to 3, you just get infinitely close to it, then y will be infinitely close to 1. So really, this whole phrase of really close to, what do I really mean by the word really? Infinite. So in calculus, instead of doing a straight-up input-output model where we say x equals 3, y equals 1, we say, what if x is infinitely close to 3? Well, then in that case, y will be infinitely close to 1. And that's the idea of a limit. Now you might immediately ask yourself, why? Why are we kind of loosening up the standard? I mean, why would you want to be infinitely close to 3 when you could just go there? Right? What's the whole point? But the whole point is what we saw earlier, right? If I do f of 3 minus f of 3, okay, in that case, I actually let this number actually equal 3. And when I did that, I got 0 over 0, which is undefined. Whereas if I let this number become really close to 3, and then I do my division, really close to 3, well then, I actually get, if I make that number really close, and I mean infinitely close, I will actually get the actual tangent slope. So that's why in calculus, we want to not just go with the strict definition of input-output. We want to talk about input something infinitely close, because that's actually going to allow us to calculate the tangent slope. So remember, if we're talking about secant slope, you have 2 points. But if you bring this point infinitely close to this point, then 2 points that are infinitely close are technically 1 point. And now all of a sudden you have a tangent slope instead of just a secant slope. So this is why we want this idea of a limit. Okay, so we also talk about approaching an x value from the right or approaching the x value from the left. So let's just say that I wanted to approach 3 from the right. Then I'm looking at a series of numbers like 3.5, 3.4, 3.2, 3.1, 3.01. So I'm approaching 3 from the right. And I'm plugging in numbers that are bigger than 3 but approaching 3. Or I could talk about approaching 3 from the left, in which case I'd be like 2.8, 2.9, 2.99999, and I'm plugging in numbers that are getting closer and closer. Okay. So this is our big conceptual idea here, is instead of just inputting the actual number, which could be problematic, sometimes plugging in the actual number leads to a calculator error or an undefined error. So what instead we want to do is just plug in a number really close to it. By really close, we mean really close. Okay, maybe I've said enough. Let's try this out. We're just going to practice this whole notion of looking at what a function is equal to if you approach it from the left or from the right. So here we go. Take a look at this function right here. We have a function. This is a very strangely behaving function because it starts over here on the left, comes down, 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 down. There's a hole right there, and then it jumps up. There's another hole there, and it continues on its way. And then what is the actual value of the function when I plug in -1, like by the table of values? Let's do a couple here. What if I plug in 1? If I plug in 1, what's f of 1? -1. And then what if I plug in -3? What's my value at -3? Now, roughly 4, right? If I plug in -4. Now, what if I actually plug in -1? Yeah, the actual value on the graph is -2, which is so nonsensical because, you know, that point is just kind of floating in space there, right? But since those are both holes, we definitely would not say that f of -1 is equal to 1 because there's no coordinate there. And you wouldn't say f of -1 is equal to 2 because there's no coordinate there. Definitely f of -1 is actually equal to -2. So this is a very strange graph, needless to say. It doesn't look like a parabola or something simple. Okay, so now let's take a look at some vocabulary. We're going to start talking about this vocabulary. And what we say here is find the limit as x approaches -1, and then this little negative sign up here means from the left. Let's just go through and read all this real quick. So this says find the limit as x approaches -1 from the left. This says find the limit as x approaches -1. What's the little plus sign mean? From the right. And then this one, find the limit as x approaches -1. There's no little symbol right there, which means from both sides simultaneously. We're going to approach it from the right and left. From both right and left simultaneously. And this last one, oh, that's a typo. That should be find f of -1. This is just regular old input-output. And this is function input. Sorry for that typo. Okay.
Find f of 1.
Find f of -1, which we already did. When you actually plug -1 into this function, the answer is -2. So we could go ahead and say the answer. No. Okay, so now let's go back and let's look at this. So find the limit of the function. Now let's just all keep in mind here, we're always talking about what's the y value. What's the y value? So when I say x is approaching -1, that's where I'm approaching on the x direction. The answer is going to be, what are we approaching on the y direction? So let's go ahead and try it. I need to be taller. So everyone take your pencil again, and instead of being a slope indicator, we're just traveling along the graph, and we're going to let x approach -1 from the left. So I'm coming along, coming along, coming along, and as I get really close to -1 from the left, what is my y value really close to? 1. So that's it. The answer is 1. I'm not saying that the y value actually is 1, because keep in mind I didn't get there. I'm just saying, as I approach along the x-axis towards -1 on my graph, so I'm approaching along the x-axis towards -1 from the left, my function value is approaching 1. Technically, is it a little bigger than 1 or a little smaller than 1? It's slightly bigger, right? Because I'm coming in from the top. So, but we still just say it's roughly equal to 1. That as x gets infinitely close to -1 from the left, y gets infinitely close to 1 from the top. So that answer is just 1. So the next one, now let x approach -1 from the right. So now, riding along my function, I'm going to approach -1 from the right. So as I approach -1 from the right, my function is getting closer and closer to 2. Technically, is it just less than 2 or just more than 2? Technically, it's just less than 2, right? Because I'm coming at it from below. But technically, if I allow myself to get infinitely close to -1 from the right, I'm going to get infinitely close to 2 from the bottom. And so we would just say the answer is 2. So again, notice we're saying, as your x value gets close to -1, what does your y value get close to? That's the same order as input-output. If x equals 1, y equals 2. Here we're saying, as you approach a particular x value, what does your y value approach? So doing this one again from the left, I would use my finger, approach from the left, and I'd say, oh, my y value is approaching 1. And then now I'm approaching from the right, and I use my finger, come up along the graph, and my y value is approaching 2. So now this next question, find the limit as x approaches -1 from both the right and the left simultaneously. I would use both fingers, and I'd say, well, what y value are my fingers approaching? Is there one single y value that my fingers are approaching? No, it's 2 different y values. So that limit does not exist. And you would write DNE, or does not exist. Which, we're saying something interesting. We're saying this function is not very well behaved, because as I approach a given x value from the right and left simultaneously, I'm not approaching a single y value. So there would be no limit. It does not exist. Now this is the first example I did with you, so if it still feels a little weird, that's okay. Let's just do more examples, and it'll become more clear as we go. But the main idea is that we approach x from the left. What does the y value approach? As we approach x from the right, what does the y value approach? If we approach from the left and right, do our fingers touch, or do our fingers not touch? Yeah, in this case, the fingers don't touch. You can even say that, fingers don't touch. No, I'm serious. That's a really good way to think about it. And then finally, this last one, this is not a limit at all. This is just the normal input-output definition of the function, in which case there actually was an answer, but you'll notice that that answer was nothing at all related to what the function was actually approaching. The function was approaching 1 from the left. The function was approaching 2 from the right. And yet, what did the function actually equal? -2. So ultimately, what we're going to say about this, we're going to use the concept of a limit to approach another concept called continuous. Very obviously, this function is not continuous. And I'll just skip ahead to share this idea real quick. What we're ultimately trying to do is define the idea of a continuous function. And a continuous function, I'm going to show you a continuous function. A continuous function is any graph that you can draw smoothly with your pencil without ever picking up your pencil. That's a continuous function because the line is continuous and smooth. A non-continuous function will look like this. It has breaks in it. It would go, and then keeps going, and then just a little hole, keeps going, starts way over here. That'd be a non-continuous function. It's what? Yeah, a little teleportation. So we're ultimately heading towards trying to mathematically define what does it mean for a function to be continuous and what does it mean for a function not to be continuous. I mean, the good news is for us that every function you've ever almost dealt with is continuous. Like f of x equals a parabola is continuous. F of x equals a straight line is continuous. So most of the functions you've ever dealt with in your whole life are continuous already. We're just going to really nail down what the mathematical definition of continuous is. Because you're not just allowed to say, draw it without picking up your pencil. But that is a very good definition of continuous. Draw it without picking up your pencil. Okay, let's try the next one. I think that was helpful to see where we're going. Now let's try it again. There we go. So now we have another graph. Now, first of all, is this graph continuous?
Yeah.
Almost.
Uh,
It's got a hole in it. Right? So we would just call that a hole. And we would call this thing a jump. This is more or less a jump as well. So no, right off the bat, we know this thing isn't continuous. What if I just said, is everything over there continuous? Yeah. Is everything over there continuous? Yeah. So it's just right here that we have a problem. So now let's go ahead and answer these questions again. What is the value of the function? So what's the limit as x approaches 2 from the left? So you bring your finger on the function, and you're coming in towards x equals 2 from the left. What is our function approaching? -2. And now, what's the limit as x approaches 2 from the right? So you put your finger on the function, you're approaching x equals 2 from the right, and y still is approaching -2. And in fact, now we take the limit as x approaches 2 from both directions simultaneously. And if we come in from both directions simultaneously, do our fingers touch? Yes, that's a very good thing. That means that the limit really is -2. Our fingers touch. So from both directions, this function is approaching the same value. Namely, the function is approaching the value of -2. Keep in mind, anytime we say the function is approaching a value, we're talking about the y coordinate, right? That's very important. The function is the y value. So whenever we're talking about the y value, whenever we talk about a function, we're talking about the y value, we're talking about the height. The function is always the height of the y value. So when we say the function is approaching -2, it is. And then finally, what's the actual value of f of 2? You plug 2 into the function, you actually get negative. Because that's where the actual coordinate is. So that's our idea of approaching it from the left, from the right, from both ways simultaneously, and then where is the actual coordinate?
so just,
Yes, Rosa?
so since find limit x to
We say find the limit as x approaches 2 from the left. Then we say find the limit as x approaches 2 from the right. Then we say find the limit as x approaches 2. That's how we do it.
so the first one is find limit x
On the left.
to the left. So is it the y coordinate or the x?
We're always asking what the y coordinate is approaching. Yeah, every time we do a limit, every time we ask the question of a limit, we're asking what is the y value approaching? And that's important.
So the 2 is basically the y as x equals 2.
Yeah, see, we already know what x is approaching. X is approaching 2, because they're telling us right here. They're saying let x approach 2. So we already know what x is approaching. On the x-axis, we're approaching this number here. But they're questioning what's the limit as x approaches 2 of the function. Now we're asking what's the y value approaching. And the y value is approaching.
We can start from whatever number the graph.
Well, yeah, I mean, you can start way out here and start going this way. The key is you just have to get close to x equals 2.
Oh, okay.
You're getting close to it by riding your finger along the graph. Yeah, that's what we mean by x is approaching 2. And you're either approaching it from the left, or you're approaching it from the right, or you're approaching it from both. Okay, good question. Anybody else? Questions? All right, let's try another one. Look at this graph. Now, just off the top of your head, does this graph look continuous? No, it's a terrible graph. It's not continuous. I mean, parts of it are continuous. Like from here to here, that's continuous. From here to here, that's continuous. From there to there, that's continuous. Then you got all these holes and jumps all over the place. So again, this is just practice to know how to read a graph and to talk about when a graph is continuous and when it's not continuous. So what's f of 1? That literally now is plug 1 into the function, and what do you get? If you plug in 1, where's the coordinate? It's not there. F of 1 does not exist. This would be a situation where you plug 1 into your calculator, hit equals, and it would say error, undefined. The coordinate is literally undefined. If you look on this graph and look for a coordinate that starts off with 1 comma something, there isn't one. Is there a coordinate on this graph that starts off with 1 comma? No. Nothing but holes all the way up x equals 1. Okay, what about the limit as x approaches 8 from the left? We're approaching from the left. So if I find 8, and I put my finger up on the graph, and I start approaching x equals 8 from the left. So again, it's very important to have your finger do this. So I'm going to be up, here's my 8, I'm up here. I'm approaching 8 from the left. What is my y value approaching? Yeah, 5. More or less 5, I like that. Technically more than 5, right? Because you're above the 5, coming down towards 5. But if you get infinitely close to 8, you're going to get infinitely close to 5. And so the answer is 5. And that's a good verbiage. If you get infinitely close to 8, you're getting infinitely close to 5. Suppose every time you do a limit, you could throw in the word infinitely close. Right? So like, what are we saying here? As you get infinitely close to x equals 7 from the right, then what does y get infinitely close to? So as I approach 7, infinitely close from the right, what does y approach infinitely close to? 6. And then the last question, as you approach x equals 4, infinitely close from both the right and the left simultaneously. That one is from the right, and this one is both. So this means you need both fingers, and you're going to check to see if your fingers touch or not. As I approach 4 from the left, as I approach 4 from the right, we're approaching different y values. Therefore, there is no limit. The limit does not exist. There's not one y value that you're getting infinitely close to. Because as you approach 4 from the left, y is getting infinitely close to 1. But as I approach x equals 4 from the right, y is getting infinitely close to 3. And so that's another DNA. One person cannot be infinitely close to the window and infinitely close to the door at the same time. Right? It's just impossible. You can't be infinitely close to two separate things. Okay. Yeah, folks. I try to think about what you're going through and what you're thinking and feeling right now. And you might be thinking to yourself, what are we doing? What is happening right now? What are we talking about? What is all this business about? Because this just sounds like some, I don't know, conceptual way to talk about a graph. Yes, Sarah? Yeah, so. Aha, very good question, Sarah. That's the whole point of a limit, is that if we were just talking about functions, if I plugged 7 into the function, it would be a hole. And therefore, it'd be DNE, does not exist. But I'm not asking for the actual function input of 7. I'm saying, just what if I get close to 7? What if I plug in 7.001? Right, that's what this is really saying. They're saying, what if we plug in not 7, but 7.0001? Well, if that's the case, if I plug in 7.001, I'm actually going to get a real coordinate, and it's going to be 5.9999, which is really close to 6, which is what the answer is. Thank you for asking that question, Sarah. That's a really good example of what a limit question even is. If we're saying approach 7 from the right, literally choose a number just to the right of 7, plug it into the function, and see what you'd get. You'd be infinitely close to 6. That's the idea of a function.
Can you explain the last one?
Yeah, first that my word is both. You were saying approach 4 from the left and the right. So here's x equals 4. If I'm on the graph approaching x equals 4 from my left finger, I'm approaching the y value of 1. But if I'm approaching x equals 4 from my right finger, y equals 3. And
why did you put your finger on there?
well, because you need to always be traveling along the graph. So watch, I'm going to travel along the graph. Like I'm traveling from one way to the other, but you're allowed to jump up and down wherever the graph goes. So if I'm moving this way and I'm approaching 4, watch me, I'm approaching 4. Okay, I almost approached 4. Now from over here, I'm going, zoop, zoop, zoop. Oh, I'm almost to 4.
Okay, okay.
Good question, folks.
Why is it?
Yeah,
That was like
these are really
always
good
a five.
questions. I'm really grateful to all of you for asking these questions, because the more we can hammer out the conceptual what's happening, the more obvious it's going to be in your head. Okay, well, there we go. We did it. So, okay, that's the concepts, folks. Those are the concepts. We're still talking about function input output. And we're talking about function input output. But instead of actually inputting a number like 5, you just input a number really close to 5. And then whatever answer you get, you see what you're really close to. Right? So, one there. See, if it was a well-behaved function, I would just plug in 5 and I'd get 28, right? If it was a well-behaved function, I can just plug in the 5, see what it equals. But if it's not a well-behaved function and it has holes and stuff, then I can't actually plug in 5. I just put in a number real close to it, and I see what I get really close to. And this is the idea of a limit. Okay. Now, now we've said all that, I'm going to show you something really cool on Desmos. So here we are. Now, recall factoring techniques. We're about to do more of our subtitle of the class, Advanced Techniques for Algebraic Manipulation. So we're about to now evaluate some limits of a formula instead of looking at the graph. So all the previous problems we just did, we looked at the graph. Right? We were looking at the graph. Now, there's no graph to look at, it's just a function. And I'd like to still do the same thing. I'd like to say, well, what's the value of this thing as I let x approach -3? This is not from the right or from the left. This is just as I approach -3. So the first thing we might consider doing is just graph it on Desmos and see what it is. And I think that's a good idea. That's what we're going to do. Let me come back to my note at the top, okay? Let's just stick with the question. I want to know what the graph, what the function is equal to as I approach -3 from the right and the left, and this is my function. So let's take a look at Desmos. When you go home and you're doing your homework on more, I highly recommend you have 2 windows open. More Desmos. More Desmos. More Desmos. All right. More money, more money. All right. So I'm going to type in parenthesis x squared plus 5x plus 6 divided by x plus 3. And here's my graph. You often have to zoom. Oh, actually, what is my graph? It's just a straight line. Yeah, that's not very exciting. It's just a straight line. Now, what do we want to approach? -3. So I'm going to come over here. I'm going to zoom in to where -3 is. And I'm going to change my window a little bit because that's such a flat line. That's not very interesting. I want to make it -10, 10. Oh, that's a little better. I'm going to go there. Don't like my graph. So here's my graph of x squared plus 5x plus 6 all over x plus 3. And we're looking at the value of -3. So first of all, where's my y-axis? There we go. Can everyone tell what value the function is approaching? That is the y value, as I let x approach -3 from the right and left. Yeah, yeah, there's my axis, right? So here's 0, here's -2, therefore this is -1. So is everyone feeling pretty convinced that as I approach -3 from both the right and the left, what y value am I approaching? -1. So everybody, you can go ahead and write down the answer. The answer is -1. Now, how easy was that, doing it graphically? Graphically, that was pretty easy. But now I'm about to show you something that's going to blow your mind. Blow your mind. Everyone, look right here at Desmos and look what's right there. Oh, snap, folks. There's a hole there. What? Have you ever seen a hole in a graphing calculator? There's a hole there. So can I plug -3 into this function? What would happen if I plug -3 into it?
Undefined. It would be
Yep, it would be undefined, and your calculator would give you an error message. So first of all, everybody, let's draw our graph. Let's draw our graph and make sure we put a hole in. So, everybody, we'll keep our graph nice and simple. Here's our graph. We know that it's at -1, 2, 3, and it was at -1. You can just draw a sloping line and put a hole there. There. Now you notice my graph. First of all, is it the most beautiful thing you've ever seen? Probably not, right? It's just a sketch. But you know what I call that sketch? Good enough, exactly right. That sketch is good enough. I know it's a line, I know it's positively sloping, and I know that there's a hole at -3, -1. Now, how did I know there's a hole there? Yeah, I cheated, right? I went on Desmos, and I looked, and I clicked on it, and I was like, there's a hole there, right? So now let's prove to ourselves, what would happen if I plug -3 into that, and I type it into my calculator? If I type that thing, something squared plus 5 something plus 6 all over something plus 3. And I go ahead and use my calculator, and I type in -3 right there. Then what's my calculator going to say? It's going to say 9 minus 15 plus 6 over -3 plus 3 is 0. 9 minus 15 is -6. -6 plus 6 is 0. It gives me the worst possible error. Yeah, 0 divided by 0, which I don't know if you're convinced yet that it's undefined, but this is undefined. So go ahead, everybody, if you want to be convinced, type it into your calculator. 0 divided by 0 is undefined. I still appreciate your point, Joshua, that, well, the calculator is just saying what it knows to say. But we should all try to convince ourselves that 0 divided by 0 really is undefined. Maybe, but I mean, what's 5 divided by 0? That's undefined. So really, we're saying anything divided by 0 is undefined. And so this happens to be 0 divided by 0 is still undefined. If you agree that something divided by 0 is undefined, then you would be able to say anything divided by 0 is undefined, and therefore this is undefined because it's something divided by 0. Even that might not be a total proof, Joshua. You still want to convince yourself. Okay, so what did we just find out? There is a hole there. So is there a coordinate right there that starts -3 comma something? No, there's no coordinate on this graph. There's no coordinate from this function that starts -3 comma 0 or -3 comma something. It's a hole. There's a hole there. Okay, so how did I get all my answers here? I cheated, and I looked on Desmos. Right, so how would I come at this same answer with just the function? And so now I'm about to tell you that answer, okay? Now the good news is, in this class, you're allowed to use your graphing calculator on your test. So you can always cheat. You can just type it in your graphing calculator, find out if there's a hole or not, where the hole is, and then you can know what the answer is. But here's the legit way to do it. So everybody start by writing it down with me. First of all, when you write down the limit notation, you actually put the x approaches -3 underneath the word limit. It's only like this because the way the computer prints it out. I mean, both are fine. If you can see either way in the textbook. But we're going to write limit over x approaches -3. And we want to approach x squared plus 5x plus 6 all over the. Now the technique for evaluating a limit is, even though I just spent all this time talking about get infinitely close to -3. Choose a number infinitely close to -3, plug it in. You're not actually allowed to plug in -3. We're talking about what is it if you're right next to -3. But the fact is, when you evaluate a limit, you ultimately just plug in -3 and see what you get. And right now, we already did. If you plug in -3, what do you get? Undefined, which tells us there's a hole. However, again, the subtitle of the class, Advanced Techniques for Algebraic Manipulation. What can I do to x squared plus 5x plus 6? I can factor it. So this might be a blast from the past. How do you factor this? You say, what do you multiply to get the last number that you add to get the middle number?
1 and 6.
It could be 1 and 6. It could be 2 and 3. We need to carefully check. If I say, what multiplies to make
2 and 3.
Do that again. I'm going to do a factor table for 6. It's either 1 times 6 or 2 times 3. It's either one or the other. But it's a positive 6, so that means that I have to multiply a positive times a positive or a negative times a negative. So what are my options really? It's either positive 1 times positive 6, or negative 1 times negative 6, or positive 2 times positive 3, or negative 2 times negative 3. Those are my 4 options for multiplying to equal positive 6. Now, out of those 4 options, which ones add the positive 5? Right, so it's definitely just 2 and 3. Okay, so now let's factor. X plus 2 times x plus 3. And what happens? X plus 3's cancel, and we're left with x plus 2. Now, because we simplified the expression, we basically just removed the hole. Because where was the hole? And what factor did we get rid of? X plus 3. That x plus 3 represented the hole at -3. You changed the signs. And now we're just left with this expression. Now we can just plug the -3 into this expression. We're not going to divide by 0 or get 0 divided by 0. What happens now if I plug -3 into this? We get -1. And do you all remember that was the answer? Yeah. Okay. Well, there we go. So that's how we evaluate a limit of a function without looking at the graph, even though you're allowed to look at the graph. Right? So this is very subtle. You're allowed to look at the graph. You have to learn how to do it without looking at the graph, even though you're allowed to look at the graph. Okay, so now let's fill in the notes up at the top. Now that we've seen how to do one problem, when evaluating a limit, you must always factor or otherwise manipulate, subtitle of the class, Advanced Techniques for Algebraic Manipulation, or otherwise manipulate the expression in order to eliminate the whole in the denominator. Well, whole / 0. Right? We can't divide by 0. This is the problem right here, this little fellow. We can't have a 0 in the denominator because then we can calculate it again on a calculator. Okay, so let's try again. Let's just dive right in here. I'm not even going to show you the graph, because if we look at the graph, it's cheating, but it's not cheating. So if I plug 5 into this, what would happen? It'd be undefined. We'd have 5 squared plus 5 minus 30, all over 5 minus 5. And if you calculate that, 25 plus 5 is 30, 30 minus 30 is 0, 5 minus 5 is 0. The whole thing is undefined. So obviously, what exists on the graph at the value of x equals 5? A whole. So if I go to x equals 5, wherever that might be, I'm just going to pretend there's my graph. There's a hole there. See that graph? I just made that graph up. But it's accurate because I have a hole at 5. Right? So even though that's not really what the graph looks like, I did factually represent the fact that at x equals 5, there's a hole. Because it's undefined. Okay, so what do we actually do then? Let's write it out ourselves. We're taking the limit as x approaches 5. That means I want to know what the function is equal to when I get close to 5, right? If I get close to 5, both the right and the left, everybody see my fingers? What if I get close to 5, but not actually get there? I just want to get close to it and see what this y value is we get. That's what I want to do. I want to get close to 5, not actually get there, because if I actually go there, I get undefined. I have no idea what the answer is. But if I just get close to 5, it'll tell me the answer. Okay, so what do? We factor, right? So everyone try it again. X squared plus 1x minus 30, all over x minus 5. Again, we ask ourselves the question, what do you multiply to get negative 30? That you add to get positive 1? So again, I think it's helpful to make a factor table. We'll make it a negative 30. I think you might be right, but let's see them all. What multiplies to make 30? 1 and 30, 2 and 15, 3 and 10, 5 and 6. They need to multiply to make a negative 30, which means you have to multiply a positive times a negative or a negative times a positive. So for each one of these, one of them has to be negative. So which one of these pairs of numbers will add to make a positive 1? Yeah, negative 5 and positive 6. Okay, so now we're ready to factor. So we say x minus 5, x plus 6, all over x minus 5, and what do we get to do? Cancel. It's always a lot more fun if you had sound effects. And then you have x plus 6. Okay, so now what is the actual limit? Now that I've eliminated the 0 in the denominator, I eliminated the whole. Now I can just plug 5 into this. 5 plus 6 is 11. And apparently, that's 11. Right? Apparently. Hey, you see my good-looking graph here? This is a good-looking graph. Even though it's not accurate, it's accurate. I know that at 5 there's a hole, and I know that as I get close to that hole, my y value is 11. What does my graph actually look like? I don't know. We can find out. We go over here and plug in x squared plus x minus 30 divided by x minus 5. Not bad, right? I mean, this was relatively close. There's my 5, and guess what's going to be there? Oh, just in case you were doubting that there was really a hole there. There's a hole. Okay, how does everyone feel about this process? Again, we have a lot of things going on here. You're allowed to use your graphing calculator to know what the answer is. But you have to be able to do it with that graphing calculator, which means you do it by factoring and simplifying. And even though when you take a limit, you're not actually plugging the number in, once you factor and simplify, you're allowed to plug the number in. It's going to tell you what the answer would be. What questions do you want to answer? Those two I call the easy ones. Yeah?
What are these limits used for?
Say that again?
What are the limits used for?
What are the what?
How are they
Limits.
Well, how do limits relate to real life? Well, because in order to do calculus derivatives, in order to even do derivatives, we have to do expressions just like we did at the beginning of class where we did f of 3.001 minus f of 3 all over 3.001 minus 3. We have to, in order to do calculus, which calculus is the bedrock of any modern science, whether it be launching a rocket or analyzing a business profit model, you have to be able to take a derivative. And in order to do a derivative, we have to be able to manage situations on a graph where you choose 2 points and bring them infinitely close and calculate the slope between them. And if you bring them infinitely close, you're really doing f of 3 minus f of 3 over 3 minus 3, which is technically undefined. But by avoiding that, by taking the limit, we're just getting close to 3 and close to 3, and therefore it's not undefined, and you get an actual answer. So, I don't know if I've satisfactorily answered your question. How do you use this in real life? It's what makes calculus work. The whole discussion that we're having about limits right now is making sure that when we go to develop calculus and take a derivative, that it actually works. And the idea is, well, yeah, that's all I'm going to say right now. Keep the question in your mind. Because I don't know if I've fully answered it yet, but we have to get closer to our goal, and then I'll be able to point back at it and say, see, Josh, there you go. This is why we needed this whole limit thing and why it's in real life. But the short answer is it makes calculus work. Okay, my phone just went off, which means we have 5 minutes. We're doing pretty good. We didn't completely finish it, and that's okay. Sometimes that'll happen and we don't completely finish it. If anything, that's good news for you folks, because that means I can't force you to do all the homework due on Monday, so I'll extend the due date. But we do have enough time to try one more problem. So for instance, number 6, is that number 6 for you? Yeah, well now everyone in the room, you can do that on your own, okay? So I'm giving that to you for homework, so maybe put a little HW there by the 6. I still expect you to do it. I'm just not gonna do it with you right now. And so same thing, what if I plug 6 into that right now? It'd be 0 over 0 on the line. So instead you're gonna have to factor the top, factor the bottom, cancel a bunch of things, and then plug the 6 in, and then you'll get an actual answer. And I encourage you to graph that on Desmos and actually zoom in and check to see if there's a hole, which there is. Now what about this one? Evaluate the limit. Do I have a denominator here? 1. Yeah, I mean the denominator is 1, but is the denominator ever going to equal 0? No, so this has no problem at all. You just plug the 3 in. So this would be 3 times 3 to the 4 minus 8 times 3. You just evaluate it. 3, 9, 243 minus 24, which is 219. That's it. I mean, in that particular case, this graph doesn't have a hole. This graph just technically is something that looks like that, and as you approach 3, you approach an answer. And so in this case, you just approach 219. No big deal. You approach it from the left, you approach it from the right, and there's actually a coordinate there. So there's nothing wrong with that function at all. And what you expect is what you get. Whereas this one, number 6, there is a hole. Gotcha.
You want a picture for all these?
Well, ideally, yes. We would draw a picture for every single problem there. Okay. So how is this? Let me just click my bearings here. So that's those problems. And then we have something a little bit trickier, 8 and 9. And then we get into the definitions of continuity. Yeah, so nobody look ahead. Don't look ahead. Don't do number 10 and 11. Don't try to do number 8 and 9. Let's just relax. Leave those for the next class period, which will be Thursday. Oh, right. Oh, we do have class on Thursday. Oh, great. Yeah, so yeah, this will still be due next week on Monday, or Tuesday, because we'll be done with it by Thursday. Okay, so folks, what should you do tonight? What are your expectations? Do more. Do all of 2.1 and as much of 2.2 as we just did. Right? Don't try to go in 2.2 up to the problem we haven't done yet, because that'd be frustrating, and I don't want you to be frustrated. Just do all of 2.1, which you can now do, and do the first few problems of 2.2. So go online. I would do it tonight while it's fresh in your mind. Okay, any other questions right now? Okay, folks, this was really good. I realize that I'm trailing a little bit, like we didn't quite make it through 2.1, And then today we didn't quite make it to 2-2. That's okay. Eventually we're gonna catch up and everything's gonna be fine. I don't wanna rush. Like I don't wanna just artificially rush us to finish by the end of a particular class day. Yeah, and your questions are great. So I'm telling you, we're perfectly on time. We're just, teeny a little bit behind, but not in a significant way. So everything's good, folks. Right now is my office hours. So any and all of you, if you want to